Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I want to join Shivani in thanking the organizers and for inviting me here. So I have to say that ranking is around 50% of the applications of this work, and the applications are about 20% of this work. So I guess I would say that ranking is 10% of this work, clustering is another 10%, and active learning is 80%. Although the original motivation for this work that sort of drove us to reach these results was ranking. And I'm hoping that the adaptive sampling or active learning techniques that I'll show here will be used for other problems as well. And I will present two problems, one ranking and one clustering. Close the door. Okay, so my collaborators are my student Owen Begleiter from Technion, Esther Ezra from NYU, and this is me. Okay, so let me start by talking about these two motivating problems. So for both problems, you have some ground set of elements. I guess if you're thinking of ranking, then these would be your alternatives. If you're thinking of clustering, then it's just something you want to cluster, a set of points. And you have n of those. And since this is a machine learning workshop, so there's an instance space. The instance space is the space of pairs of these elements. Okay? So in the first problem, which you can call a ranking or ordering, you want to learn an order relation or a ranking over the set V, over the ground set. And instead of writing the exact mathematical definition of that, I just mean I want to learn a matrix that looks like this, where the rows and columns are indexed by V. Okay, so HUV equals 1 if U beats V, if U is ahead of V in this order relation, and it equals 0 otherwise. So it's an antisymmetric matrix, HUV equals 1 minus HVU, and you can ignore the diagonal. Okay? So it's not only antisymmetric, but it's also transitive, meaning that it induces a linear order. Okay, so if you know what this permutation is on V and you permute the rows and columns of this matrix H, which you are looking, it should look like this. Okay, of course, if you don't know what the order is, okay, and you just randomly permute the rows and columns of this matrix, it's not a predicate. Okay, it doesn't look like this. So that's the first problem, and I think a permutation matrix was mentioned here earlier today. This is a matrix where you have 1 in every column and every row, and the rest is 0. Okay, so this is a different representation of a permutation. Okay, it's not the same representation. Okay, this matrix is the preference relation matrix. The second problem is that you want to learn a K clustering or an equivalence relation over your ground set where there are at most K equivalence classes, in other words. Okay, so you're looking to learn a function, call it again H, hypothesis, from the set of pairs to 0, 1, where 1 means in the same cluster, 0 means not in the same cluster. Okay, in other words, you're trying to learn a matrix which, after renaming the rows and columns properly, would look like this. You have K blocks of 1s and the rest is 0. Okay, and notice that this is a symmetric matrix, so HUV equals HVU. Okay. Now, if you think of this as a graphical, learning some kind of graphical object, then in the ordering case, if this is the set V, then you're trying to learn a tournament or a complete directed graph over the set, okay, where HUV equals 1 if the edge points to V and 0 otherwise. And you're trying to learn a consistent transitive tournament, okay? So this is a possible solution in the space of solutions. All the arrows point right. Okay? And in the clustering, okay, you're assuming that your data is partitioned into at most K cliques. Okay? And H tells you whether there's an edge or not. So HUV is 1 if there's an edge, 0 otherwise. Okay, so in this example, k equals 2. Okay. Okay, so what is the input to this problem? Of course, it's the object you're looking for plus some noise. Okay, so for the ordering problem, the only thing you're assuming about your input, which is a binary matrix, is that it is anti-symmetric. Okay, up to this 1. Okay, so if the input is y, then yuv equals 1 minus yvu. Okay, and ignore the diagonal. Okay. But of course, you may have noise, so it can look like this transitive preference matrix plus these chicken pox ruining the order. And for clustering, you're just assuming that the input is symmetric. Okay, so it may look like some ground truth clustering plus some noise. Okay, and of course, the integer k is also part of your input. So the objective is to minimize the loss of your output h, so you're allowed to output only something that's consistent, either a transitive ordering or a transitive equivalence relation. And your loss is the L1 loss between the two matrices. I just mean the sum, half of the sum of the pointwise loss each matrix element. Okay? Now, we're going to settle for a 1 plus epsilon approximation, multiplicative. So if the optimal solution has value, loss value opt, then we would settle for a 1 plus epsilon times that. Notice that it's multiplicative. So the epsilon is a relative regret, not an absolute regret, as often used in machine learning. And we're also settling for a high probability of success. So we are allowing ourselves to succeed with probability 1 minus delta. And this delta will disappear because I'm going to assume it's inverse polynomial in n. Okay, so we'll only have n as a parameter. Okay. What are the resources I care about? So when I did my PhD, I studied these two problems only from the computational complexity point of view. Okay, and then certain results were found by myself and by others, and then that was sort of the end, and I got turned off, and then I realized that there's the whole world of query complexity, which is in fact basically machine learning, and I started studying these problems from that point of view. Okay, and this is what I will concentrate on today. Okay, but let me just quickly show you what is known from a computational complexity point of view. Okay, so what do I mean by computational complexity? I mean queries cost 0. Okay, the input is given to me for free. The matrix Y, which was the input, the noisy ordering or the noisy k clustering is given to me. Okay, so if you take this extreme, cost 0, then this just becomes a combinatorial optimization problem. Okay, you're looking to find the consistent matrix, a transitive matrix, either transitive in the ordering sense or in the equivalence relation sense, it doesn't matter, that minimizes this loss. So first I'll say that both problems are NP hard. I didn't put that as a bullet. And both admit a polynomial time approximation scheme for a fixed epsilon. What does that mean? It means that for any epsilon that you give me, say epsilon equals 0.01, I can give you an algorithm that will run in time n to the million, say, but a polynomial in n, and will give you a solution with that approximation guarantee, 1 plus epsilon. Okay? And these are the authors of these papers, of these results. And unless you think that P equals NP, you can't do better. So that's as far as you can go pretty much as far as computational complexity in the worst case. Okay? So what about query complexity? Okay. So there exists an algorithm with expected query complexity order of n, sorry, it's supposed to be uppercase n log n, for epsilon equals 2. In other words, I can give you an expected 3 approximation solution to both problems. actually, okay, for ordering for now, with a query complexity order of n log n, meaning I only view this many entries in the matrix expectation. Okay? So that's sublinear in the size of the input because the input is of size n squared. The running time also happens to be that, doesn't really matter. For clustering, there's a similar result. Okay? If you want a multiplicative approximation of 3, 1 plus epsilon equals 3, then you can make do with querying order of nk, where k is the number of clustering. It's very easy. Both results are very easy to show if the optimal loss is 0, meaning if the input is already consistent. In order to show this in the general case, you need to read this paper by myself, Charikar and Newman in 2005. And I'll tell you, I'll just, spoiler, the algorithm you run for the ordering case is quicksort. Okay? So it's quicksort on non-transitive data. It turns out that if you do that, then the algorithm terminates and it gives you a permutation. And this result shows that it has some guarantees in terms of approximation. Okay. Okay. So again, my motivation now is look at query complexity issues. Okay. So our space of solutions is binary functions over the set of pairs. Okay. X, the instance space, was V product V, the ground set product itself. You exclude the diagonal. The loss function that I defined was the typical binary loss function in machine learning. You pay a penalty if you don't guess the bit correctly, you pay 1. If you guess the bit correctly, you pay 0. Okay, I didn't normalize. I just wrote the loss as a sum over all matrix elements. But in fact, if you want to use probability, if you want to assume that there is distribution over the instance space, as you always need to in machine learning, then you can just assume a uniform distribution over the set of pairs. So up to this normalization, you need to divide by n squared, right? It's exactly what you would define in machine learning. Okay, so once you have a binary classification problem, the first thing you ask is what is the VC dimension of the space of hypotheses? Okay? And it turns out that the VC dimension is n minus 1, where n is the number of elements. Okay, so this is a really simple exercise. Why is it so? Okay, so you remember from the definition of VC dimension, you need to find the largest set that you can shatter, right? Now, if you take a set of unordered pairs UV, you induce an undirected graph. If you take n pairs, then this graph will contain a cycle. And if you have a cycle, you can't shatter it. For example, in the ordering case, you can't direct all the edges in a circle. Okay? So you cannot shatter a set of size n, which means the VC dimension is at most n minus 1. It's a very simple exercise. Okay, so now we're going to plug in these bounds, the VC dimension bound, into whatever theory we have about VC dimension. Okay, so using empirical risk minimization principles, if you want to get a regret of mu times n squared for any mu, okay, regret, I mean the optimal loss, the loss you get minus the optimal loss, then you need order of, there's some logs missing maybe, order of VC dimension, which is n or n minus 1, doesn't matter, over mu squared queries into the input y, where these queries are chosen uniformly at random from the space of pairs. Okay, this is just standard textbook statistical machine learning. But our goal was to get 1 plus epsilon opt. Okay, notice that this is an absolute regret, mu n squared, and I want a relative regret. Why? Because we'll see soon that we can do that. Okay, but let's see what happens if you just use VC dimension theory. Let's say opt equals n to the 3 halves. Okay, so if you want 1 plus epsilon opt loss, then in the notation of mu, in the absolute regret notation, we'd need to take mu to be equal to epsilon times n to the minus half. Now you plug this mu in the query complexity expression, you would get something like n squared. But n squared is the size of the matrix. So this isn't informative. In other words, VC dimension theory breaks down once opt is below n to the 3/2. It doesn't give you anything non-trivial. Okay, so something is wrong. And the reason something here has to be suboptimal is seen if you take the extreme case. So what is the extreme case? The extreme case is when optimal solution equals 0. Okay, meaning in the ranking problem, if you want, the input is already a transitive preference function. But then we know that by doing something like quicksort, okay, with query complexity n log n, again, it's supposed to be capital N, I apologize for that, you can get the exact solution. Okay, and definitely not n squared. Okay, so somehow we believe that as opt becomes smaller and smaller, life should be easier and not harder. Okay? At least that's what happens in the extreme case. Okay, so what's wrong with the VC dimension argument? Okay, so one possibility is that the VC dimension bounds are pessimistic compared to real life, and that could be one problem. The other problem is that the VC dimension approach is passive. It is not active. It is not adaptive. Okay, and you can argue that any algorithm that does not choose pairs, does not query adaptively, is bound to fail. Okay, it's clear by this I mean that you can think about it for 10 minutes, but not that if queries are chosen uniformly at random, IID, okay, in fact you can replace this IID with anything that is not adaptive. If your querying strategy is not adaptive, okay, then in the extreme case, when say opt equals 0, you're going to need order of n squared queries in order to recover the solution exactly. Okay, so the problem with the VC bounds is not in the VC bound, but in the fact that the querying is non-adaptive. Okay, so once you understand that this is really an active learning problem, okay, what does it mean active learning? It means that I'm going to query the instance space, yeah, the set of pairs, based on some notion of informativeness that I compute. Okay, and not just IID based on some distribution. Okay, so you go to the machine learning literature and look for general bounds, statistical learning bounds using active learning. And the most general thing I could find sort of follows these lines. Okay. So assume you currently have a solution H with some loss, call it alpha. And assume you know this loss. I mean, you don't really know, but let's assume that you have maybe some bounds. Here I'm going to assume you know it exactly. Okay, so I'm going to derive some kind of descent algorithm. I'm going to improve the solution by doing some clever querying. Okay, so I definitely don't want a worse solution in the next iteration. Okay, so what does this mean? I can consider only solutions, call them H prime, for which the error, the loss, I mean, is also at most alpha. Okay, it's a small space of solution. It's called the version space. Now, by triangle inequality, all such solutions satisfy, did I define the distance? I did not. That the distance between H prime and the current solution is at most 2 alpha, where the distance was just what I showed earlier, the L1 difference between the matrices. Okay. This is just by triangle inequality because both solutions are at most alpha away from the input y. So, okay. So in other words, we can consider the space of solutions, okay, which is the ball of radius 2 alpha around the current solution we have. Okay. So we can sort of shrink the version space, the space of possible solutions. But once we do that, we can also shrink the space of instance, the instance space that we can consider. Okay? In particular, we can decide to consider instances, a set which depends on H and alpha, on which the version space is not unanimous on. What do I mean by that? If all hypotheses, all solutions in the version space, okay, have the same belief about the value of H, of the matrix, at a certain UV, okay, then there's no need to query that pair from now on. Okay? This means they're all unanimous on it. Okay, so here's a little picture. This is the solution space, okay, space of transitive matrices. And this is the instance space, the set of pairs. Okay, so we have some solution H here. This is the optimal solution H star. And this is the ball of radius 2 alpha around H. As you can see, it contains H star. We're not throwing away the optimal solution. Now this H, this solution, thinks the value of that instance is, the color's not very good, is 0. While this one thinks the value is 1. Okay, the one is enlarged, so they're not unanimous on it. Okay, so this point is included in the set XH alpha. On the other hand, all these solutions agree that on the value of these points, of these instances. So they're outside the set XH alpha. I don't care about them. No need to query them. Okay, so this region of points on which the version space is not unanimous on is called the disagreement region. Okay, it has a name, and it's a great name. And then you sort of ask, what is the size of the disagreement region? The smaller it is, the better off you are, because you probably need to query less. Okay. So there is an invariant, okay, it's an invariant of the concept class, the space of solutions, called theta. Okay, it's called the disagreement coefficient. Okay, this is all literature from general active learning theory. So theta measures the rate of growth of the disagreement region as a function of alpha. Okay? The lower it is, the easier it should be to learn in terms of query complexity. And this is indeed the result. So theta is defined as the supermem over all alpha, alpha greater than 0. You take the supermem over all possible solutions H of the size of the disagreement region divided by alpha. Okay, you want to know what the grade of the worst rate of growth is. And once you have this definition, okay, then you have two parameters. One is the VC dimension, okay, denoted by D, and the second is the disagreement coefficient, denoted by theta. And then you can show that the query complexity. Okay, now I'm going to be careful. I'm going to assume epsilon is constant, say 0.001. Okay, but the query complexity becomes D times theta. Okay, in our case, it's log n, but in general, it's log square of 1 over epsilon, which I'm assuming is constant. So you can ignore that. Roughly D times theta, even as opt goes to 0. Okay? So in the standard VC theory, when opt goes to 0 and you want a relative error, then the query complexity explodes. Okay, and here it doesn't explode. Okay, so that's nice. So let's try to compute this disagreement coefficient for the problems we have. And by the way, this is Steve Haneke who championed this theory of disagreement coefficient. So it turns out that in our case, the disagreement coefficient can be computed, and it equals n. the number of alternatives, the size of the ground set. Okay, the proof, I'll skip it. It's not very difficult. But then you plug it into the bound on the query complexity. You get the VC dimension, which is n minus 1, times the disagreement coefficient, which is n. You get order of n squared. So again, you get the result you get is that you need to query the entire input in order to get something. I mean, we knew that without any theory, right? Okay? Okay, so something is not efficient enough in the theory of disagreement coefficient. So we need a better sampling idea, and I'll show it to you now. Okay, so again, this is a descent algorithm, meaning that at each iteration, I will obtain a better solution than what I had earlier. Okay? So I'll have a version for the ordering and the version for the clustering. Okay? Okay, so I have a solution H. H is a permutation. It's an ordering on the ground set, which means that it induces a position function. Okay, for every element in the ground set, the position of the element is 1 if it beats all the others, and it's n if it's beaten by all the others, and then you have all the positions in the middle. Okay, it's a natural position function you would define. Now sample some pairs. By sampling pairs, I mean accessing the input y, the label function y on these pairs. I'll sample this many. See, it's n polylog n divided by epsilon cubed. Call these pairs u1, v1 through uq, vq. Okay? I'm going to sample them IID, but I'm going to create a bias in their sampling probability. So what is the bias? The probability of choosing, sorry, for each I. Okay? There's a distribution which governs how I choose ui, vi. So the probability of choosing any given elements, u and v, is proportional to the inverse of the absolute difference between their positions. In other words, the closer they are in my current solution, the higher the probability that I'm going to select them. Once I define such a distribution, then I can define an empirical loss over this distribution. So the loss with this hat of any other solution H prime is the sum of these mistakes over all the elements that I chose. And now I need to do some kind of unbiasing, because I chose them with different probabilities. So the way you do that is like, there's just one way to do that, right? You multiply for each element in the sum by the inverse of the probability of having chosen the pair in that sum. Okay, it's supposed to be ui, vi here. Okay, and then you normalize here somehow. Okay, so there's really one way to define this empirical loss. And before I go to the next iteration, I replace my current solution with the minimizer of this empirical loss. Okay, so this is an empirical risk minimization approach, except that I'm defining an empirical process which is biased, okay, using the previous solution that I had. Okay, notice this is an NP-hard problem, okay, but this is, I'm looking at the extreme scenario. I care only about query complexity, and I don't care about computational complexity for now. Okay, there's all these NP hardness issues. You're going to have to use some kind of heuristic anyway, because, you know, NP hardness theory says that you're going to need to run an algorithm in time n to the 1,000 anyway, so I don't care about that. Okay, so like I said, in this bias, you give more weight to close pairs in your current solution. And this is, in fact, something very natural. And there have been papers on this problem which define active learning heuristics based on this idea. Okay? But as far as I know, this is the first proof of some guarantee, which I'll show you in a second. So what do you do for clustering? So for clustering, you choose this many pairs. So there's n log n, and then there's some mixed ugly expression in k and epsilon. K is the number of clusters. So you need the maximum of k squared over epsilon squared, k over epsilon cubed. Doesn't really matter. And now I need to tell you what the bias is. Okay? So here's how the bias goes. I'm not going to choose u and v uniformly at random. I'm going to choose u uniformly at random from v, from big V, the set of the ground set. And how I'm going to choose v, I'll choose it in a two-stage process. First, I'll choose a random cluster from the clusters induced by h, because my current solution induces a k clustering. And within that cluster, I'll choose a random element. In other words, if you think about it, you give more weight, when you choose v, the other guy, you choose more weight to small clusters than to big clusters. And that's also a very intuitive thing to do. Okay? Because the small clusters is where you need to query more in order to know what's going on. So what is the guarantee that you get from this sampling at each iteration? So with probability 1 minus inverse polynomial in n, so you have a fixed solution h. Okay? So for every other solution, h prime, you have this guarantee. Okay, so what does it say here? It's really, it looks kind of complicated, but it's not really. This expression is the loss of h prime minus the loss of h. So it's the loss calibrated so that h would have value 0. Okay? This expression is the empirical version of this expression. Okay? It's an unbiased estimator of that. Okay? So then you measure how well this empirical number that you compute, how far is it from the actual thing you want to compute. And it's at most epsilon times the distance between h and h prime. Okay, so the closer h prime is to h, the better your approximation. The further it is, the worse it is. Okay, so the approximation degrades gracefully as a function of the distance between h prime and h. And this happens uniformly for all h prime. Okay, with high probability. Okay, so this is the main technical lemma. As a consequence, and this is something you can convince yourself, and I don't know, also, I guess it's also an exercise. If h1 is the minimizer of the empirical loss, which is what we did in this algorithm, then the regret of h1 is at most the previous regret times epsilon, okay, plus an O of epsilon times opt. Okay, so you slashed the regret by a factor of epsilon. Okay, and then you have something additive, but this is unavoidable. Okay, and as a corollary of that, after t iterations, the regret of the tth solution, so h time will minimize the empirical loss that you created from h1, h3 from h2, and so on. The regret you'll have after t iterations is at most epsilon to the t times the original regret plus this unavoidable term. Okay, so you can see there's an exponential rate of learning as a function of the iteration. Okay, 5 minutes, great. Okay, so the conclusion from if you want epsilon times opt in the end, so you want t to be something logarithmic. The original regret was at most n squared. Okay, so you sort of figure what the number of iterations should be. And then if you remember from the previous slide, which you probably don't, but I can tell you what the query complexity in each iteration was, you multiply those two numbers, you get that for ordering, you need roughly n log cubed n over epsilon the third to get epsilon times opt, regret, or to get 1 plus epsilon multiplicative loss. And something similar for clustering, but involving k. Never mind. Okay? Now if you think of epsilon as constant, okay, epsilon equals 0.01. Okay? So you have n times polylog n to get 0.01 times opt, and it doesn't matter if opt tends to 0. Okay? This does not explode. This does not get close to n squared. So how do you prove this? Okay, so I'll just show the overview of the proof. So first of all, the first thing you see, okay, so the thing you want to prove is this. Okay, this guarantee, which shows that this empirical process has good properties in terms of approximation. So the first thing you do is some kind of Chernoff bound to show that this empirical loss does not deviate too much from what it's supposed to be, and then maybe union bound to argue against all possible solutions. But this fails because the solution space is too big, or the failure probability is too big. Depends how you see it. Okay, so you need to do something slightly more clever. So there's two main ideas. One idea is called charging. And the way you do this charging is, so if uv is an inversion in h, okay, you want to argue uniformly for all h prime. So if uv is an inversion in h prime with respect to h, then you want to charge it either to u or to v. The way you decide is you see which element traveled a longer distance from its position in h to its position at h prime. Okay, and you charge this inversion to this element. Once you define this charging, meaning you say for every pair uv in which there's a disagreement, which one is to blame for this disagreement, you write the loss as a sum over all u. So it's a sum over uv, the loss, right? So I'm going to batch expressions together. So you sum over all u, and you sum over all v in the charge of u. Okay? And then you have this expression for every u. Okay, once you have this new decomposition of the loss, then you indeed do a union bound over some Chernoff, it's a Bernstein type deviation bound, but you do it over a small set, and this family of structures over which you do this union bound is described by the charge sets. So how the charges of pairs are distributed among the elements. So that's one idea you have. For the ordering, you need another idea, which is called Diaconis-Graham theorem, connecting the Kendall-Tau distance and the Spearman foot rule distance between permutations, which I don't have time to describe, but it's a classic lemma related to combinatorics on permutations. So what are the conclusions? So we studied two learning problems which beg for active learning treatment. Okay, anything which is not active is just not going to be optimal. General purpose active learning ideas fail, and I showed you why. And an iterative algorithm with sampling bias depending on solution from current iteration works. The question is just how to create this bias. And the goal was to get this approximation inequality for a related empirical process. As far as future work, I want to mention work by Shu and other guys. So they actually also studied this problem of k-clustering learning, but they wanted polynomial. They wanted two things. One of them was, and correct me if I'm wrong, was polynomial time algorithm. Okay, but this is an NP-hard problem, so of course you assume that the noise on the input is stochastic or satisfies certain structural properties. And then they show that using the robust PCA theory, which many of you know of, you can do this if you replace your loss with something called trace norm of your solution, which also many of you know, plus L1 as a surrogate for rank plus sparsity. Yeah, I noticed that in clustering, the solutions you look for are matrices of rank at most k, right? Okay, so it's a very natural way to do this. The query complexity in the result, and now correct me if I'm wrong, degrades as the true clustering becomes more unbalanced. Okay, as the ratio between the largest cluster and the smallest cluster is bigger, the more you need to sample from the input in order to solve it. Given these results, this degradation seems either unnecessary or it seems like it should be capped by maybe some function like log k or something like that. Okay, so this is one open problem which I'm working on, and I hope Shu's not working on unless he's working on it with me. And I'll be happy to talk more about it later. And then once you have this result, you also can ask similar questions about convex relaxation a la trace norm plus L1, but not for clustering, for ranking. The problem is that the family of matrices that I showed here, these upper diagonal 1, lower diagonal 0, is not low rank. Okay? So that's sort of unfortunate. On the other hand, it has a low numerical rank. Okay? Numerical rank is sort of this relaxation of rank, and the numerical rank is roughly log n. Okay? So it seems like there should be also something possible there in the line of the robust PCA type of work. Also interesting problem I'd like to study. That's it.
Any questions? Coffee? So can you explain more how the robust PCA is useful for this?
Yeah, okay, so notice that in my talk I ignored computational complexity, which is why I didn't care about convexity of the loss function. Okay, this was only in the last slide, but I guess it's of interest to, I mean, many people here do optimization, so of course you care about that. So you're looking for a solution, okay, which looks like a block diagonal matrix with at most k blocks, and they're all full of ones. So you're looking for a matrix which has rank k. Okay, so if you subtract this matrix from the input y, which is a noisy version, you expect to get a sparse matrix, because you assume that the noise is rare. Okay, so what you're trying to recover, you're trying to explain y as a sum of two matrices, one low rank and one sparse. And then you convexify that by saying that instead of low rank, you'll take low trace norm, and instead of sparse, you take low L1.
Okay, so you just say, instead of doing PCA or finding the eigenvector just in this very framework, right? Just combine the two?
Yeah.
Okay.
Yeah, you just use this framework, and then there's also the framework of the, okay, that's robust PCA, but you don't have the entire input, so then you need to use tools that we use in the Netflix problem, where you also choose which places to see in the matrix randomly. Okay, so you have.
Because usually when you do these clustering ideas, they're usually quite robust actually. When you find because of the way the weights are. So I'm not sure how much this adds. But
okay, I'm not sure where the weights.
But we can talk about it after.
Okay.
So, okay.
Any other questions? So it's time to speak up.
Oh, yeah.
Is there an efficient algorithm for H dash needs?
Is there? No, it's actually, in the worst case, it's NP hard. In fact, it's harder than the actual problem that I defined, assuming you have the entire input, because this is a sparse, this is something called, in combinatorial optimization, it's called minimum feedback for the ordering case. You have a directed graph and you want to order the vertices so all the edges point right, or as many as possible. Okay? If you're assuming that your input is a tournament, meaning you have for every pair, you have an edge in some direction, then it's NP hard, but it's easier than in case where the graph is sparse. Okay, and notice that between iterations, you chose a sparse set of pairs. So it's actually a sparse version of minimum feedback arc set. So in the worst case, it's known to be notoriously hard. Like you can get a log n approximation multiplicative, and not better than that probably. But then the pairs which you choose are chosen randomly using some process. So I'm not sure about the computational complexity of that particular instance. But I would bet that it's still NP hard at least. Okay, so yeah, I mean that's the problem when you take the extreme. I mean, I took the other extreme of the spectrum. I abandoned computational complexity because I don't care about improving an algorithm that runs in time n to the 1 over epsilon squared to n to the 1 over epsilon. I mean, if epsilon is 0.1, then who cares? You know, I'm turned off. I don't care about that anymore. So, you know, the other extreme is that you throw that. You're assuming that you're going to need heuristics in each step anyway, for a computational purpose. And then you ask about the query complexity. And yeah, and somehow for these two problems, I mean, okay, so what does it mean query complexity? I mean empirical risk minimization argument. I don't care about computational complexity. I just care about what rate my empirical loss uniformly converges to the actual loss, right? And it turns out that for these two problems, active learning, I think active learning should have been defined from these problems, in fact. Somehow it came from other directions. I mean, it's a natural thing. But these problems really beg for active learning treatment in machine learning. And